Hi everyone. Today let us discuss about constraint satisfaction problems. So it deals with solving problem by identifying constraints and finding the solutions which satisfies these conditions. The basic components of CSP are variable, domain, and constraint. Variables are items that need to be determined. It represents the unknown variable in the problem. So for example, a Sudoku. So in Sudoku, each empty cell is a variable. In timetable, each the class period is a variable. In map coloring, each state or country is a variable. Next, domain. So domain describes the set of possible values that a variable can take. So domain may be finite or infinite, depends on the problem. So in Sudoku problem, so domain has a finite value, so it's from 1 to 9. Whereas in traffic light, there are three domain values, red, green, and yellow. So in Boolean variables, there are only two domain variables, true or false. Constant is a rule that restrict which variable value the variable can take. So it ensures that the final solution is valid. Example Sudoku. So there is no repeated number in any row or any column or 3 cross 3 box. Map coloring. Adjacent state or country cannot have the same color. Timetable. A teacher cannot teach two classes at the same time. The types of constraints. So constraints can be classified into various categories. Unary constraint, binary constraint, global constraint. Again, global constraint is classified into two categories, all different constraint and some constraint. So what is unary constraint? So which limits the possible values of single variable. So it is the easiest constraint to find. It has only one parameter. For example, the expression x1 is not equal to 7 means the variable x1 cannot have a value 7. So binary constraint which involves two variables. So it describes the relation between two variables and consists of only two variables. For example, x1 less than x2 indicates x1 must be less than x2 in order to be true. And global constraint. So in contrast to unary and binary, global involves more multiple variables and impose more complex relationship between them. Uh, it's often used in CSP to capture high-level pattern, structure, and rules. It is further classified into two categories. That is, first one is all different constraint. So all different constraint occurs each variable each variable has a unique value. So, for example, the expression all different x1, x2, x3 ensure that the values of x1, x2, and x3 must be unique. Some constraint, some constraint occurs. Some of the values assigned to a group of variable meet a particular requirement. So, for example, sum of x1, x2, x3 equal to 15 means sum of these values is equal to 15. Then map coloring. So, for example, formulate the map coloring problem for the map of Australia given below. So CSP formulation for this problem is first let us see the take the key components variable, domain, and constraint. So the variables. So these are the variables. So here each variable represents the state or territory of Australia, and the domain are green that is given in the problem. Red, green, and blue. Each variable has a unit that is same domain of three colors, and these are the constraints. So each constraint is a binary constraint that states two adjacent regions must have different colors. And what is the constraint? Two adjacent regions should not have the same color, no matter whatever the color we are choosing. So the goal is to assign a color to each region so that the neighboring region should not have the same color. So here the domain we can use only red, green, and blue, so such that the adjacent regions have different colors. These are the variables. So the states of Australia are the variables. So there are six variables: Western Australia, Northern Territory, Queensland, Victoria, South Australia, and Tasmania. Domains are three variables are there, red, green, and blue. Constraint, what's the constraint? So adjacent regions should not have the same color. So must be different colors. For example, Western Australia should not be same color cannot be used for Western Australia and Northern Territory. Let us start from the beginning. So here there are three colors. So if you are using a red here, then the next region for next state we should use either red, uh, sorry, green or blue. If it is red, then next region can be either green or blue. If it is green, then the next region should be blue only. Okay, so then if it is the red, then here we should use only blue. If it is blue, then here we can use only red. Like that we can backtrack the color, and this is the final state. So the solution is for Western Australia we have used red. Northern Territory we used green. Queensland red is used, and for South Australia blue color, Victoria blue, Tasmania red. So these are the different colors used for the given map. The next one is Minmax algorithm. So Minmax algorithm is used to find the utility values and the best strategy for max. So let us take one this example. So where A is the initial state of the tree, and we are going to solve the problem in three steps. The first step is game tree is generated. Okay, so here the game tree is given in the problem itself. Then find the utility values. So here the utility values that is given here, the terminal values or utility values are given in the problem. Then backtracking. So first we have to find the values. So suppose maximizer. This is we will assign max and min alternatively for the nodes. So here A is parent node, and for A, B and C are the child nodes. For B, D and E are child nodes. For D, H and I are child nodes. For E, so J and H are child nodes. For F, so these are the child nodes, and G is parent for N and G, and C is parent for G and F. Similarly, we can have. Okay. So minimizer first, minimizer will take the turn. So which has the initial value of the maximizer is minus infinity. So minimizer, the maximum value of the minimizer is plus infinity. Uh, Let us start from in this side. Okay, so as it follows breadth first search method. So A is the parent node for A, B and C are the child nodes. Then we have to find the value for B. How do you find the value for node B? So again it has two child nodes, D and E. If we have these two values, then we can find the value of B. So how do you find the value of D? So this is the maximizer. Find the maximum value from these two. How do you find the maximum value? So first we compare this value with maximum value. What is the maximum value? Minus infinity. So minus 1 is compared with infinity, minus infinity. Then what is the maximum value? Minus 1. Then that minus 1 will be compared with 4. Then out of these two, the maximum value is 4. That will be returned to node D. Similarly, for node E, this two the utility value for node E, J and K are the child nodes. This value 2 is compared with the maximum value. What is the maximum value? Minus infinity. So minus infinity, among minus infinity and 2, 2 is the maximum value. Then 2 is compared with 6. Then maximum value of these two is 6. Now D and E we have values. Then we can calculate the node value for B. How do you calculate? So B is for node B we have to find the minimum value. So what is the minimum value? So first you compare 4 with the minimum value, that is plus infinity. So what is the minimum value? 4 is the minimum value. Then this 4 is compared with 6. Among these two, 4 is the minimum value, that is passed to node B. Then Similarly, for node F and G, we have to find the minimum and maximum value. For node F, minus 3 is the maximum value, and for node G, 7 is the maximum value. So then, find the node value of C. What is the node C? So minimum is so find the minimum value of C. What is the minimum value among these two? So among these two, the minus 3 is the minimum value. So for node C, what is the node value of C is minus 3, and node value of 4 is B is 4. Okay, so this side we are getting 4, this side minus 3. Then what's the maximum value? 4. So for node B, the maximum value is 4. So best strategy is 4, A, B, D, and I. Okay, so 4. So here, what is the value? 4. Here also 4. Here also 4. Here also 4. So what is the difference? The difference is 0. The difference between this is 4 and this is also 4 means what is the path cast? There is no path cast. And here also this is 4 and this is 4 means there is no path cast. And here also there is no path cast. So best strategy is A, B, D, and I. Okay, so what is the winning score? 4. So this is how we can perform the Minmax algorithm. Uh, the next type of algorithm is alpha beta pruning. So alpha beta pruning is an optimization technique for Minmax algorithm used in decision making and gaming theory, which makes Minmax algorithm more efficient without affecting the final decision. So in Minmax algorithm, the number of game states has to be increased as the depth of the tree is increased. The number of game states will be increased in a exponential way. Alpha beta pruning is a modified version of min-max algorithm. So here without checking each state, we can compute the correct min-max decision. So hence it is called pruning algorithm. The alpha beta pruning remove all the nodes which are not really affecting the final decision but makes algorithm slow. So by pruning these nodes, the algorithm works fast. So this method involves two threshold parameters alpha and beta. The two parameters alpha is the highest value. So the initial value of alpha is minus infinity and beta is the best lowest value choice. The initial value of beta is plus infinity. What is the condition for alpha beta pruning? So the main condition is alpha should be greater than or equal to beta for any node. Let us see one example. Alpha beta pruning. Find the node values with the help of alpha beta pruning algorithm. So first, this is same as min-max algorithm. This is a parent. A is parent for A, B, and C are the child nodes. And for D and E, B is the parent node. For F and G, C is the parent node. Okay. So first, let us assume max, then min, then max. So here these are the terminal values or utility values which are given in the problem. So first, let us start from how do you find? So let us start from this one. So D. Okay. Uh, Sorry. Let us start from parent node. So for parent node, what is alpha? This is since it is maximum node. Alpha is minus infinity and beta is plus infinity. For a maximum node, for the alpha value of alpha should be calculated. For minimum, beta should be calculated. Here the alpha beta will be transferred to the child node and the node value will be transferred to upper node. Alpha equal to minus into beta equal to plus infinity will be transferred to child node B. Okay. So then what is B? B is nothing but the minimum node. So the minimum node means beta should be updated. Then same value has to be transferred to node D. So in node D, what node D is maximum node. So alpha should be updated. So how do you update alpha? So alpha is the maximum. So alpha equal to minus infinity. So find the maximum value. So minus infinity is compared with 2. So what is the maximum value? 2 is the maximum. Then the 2 is compared with 3. So among these two, 3 is the maximum value. The node value of B is 3. So alpha equal to 3. Okay. So then we have the value is now the node value of D is 3. So that is move to the upper node B. So now the node value of B is also 3. So here it is the minimum node. For node B, we have to update the value of beta. How do you update the value of beta? So here again we just find the minimum value. So my 3 is compared with plus infinity. Then what is the minimum value? Minimum value is 3. So beta is updated with 3. Then this value is passed to this alpha beta will be passed to the child node E. So here alpha is minus infinity for child node B. E alpha is minus infinity and beta is 3. So here again this is a max node. So alpha should be updated. How do you update alpha? So again take the maximum value. Alpha means maximum value. So here what is the maximum value? 5. That is minus infinity is compared with 5. Then alpha will be 5. Beta is 3. So what is the condition for proving alpha greater than or equal to beta? So when the alpha is greater than or equal to beta, then the subsequent child node will be proved. So here the node value of E is 5. So then this path is proved. Then this value is transferred to node A. What is the value of beta? 3. So that is transferred to node A. The node value of A is 3. So now for node A is maximum node. Then the value of alpha should be updated. What is alpha? Alpha is maximum value. So already the node value is 3. That minus infinity is compared with 3. Then that is equal to maximum value is 3. So alpha is 3 for node A, alpha is 3, beta is infinite plus infinity. So this alpha and beta is passed to node C. So at node C, what is alpha? Alpha is 3 and beta is plus infinity. Then the same value will be transferred to node F also. And then for the node C, alpha is 3, beta is infinity. This alpha beta values are passed to node F. Okay, then we have to find the node value of F. How do you find the node value of F? Just take this is the maximum node. So find the maximum value among these two. So what is the maximum value? 1. So this 1 node value will be moved to upper node, that is C, and alpha is 3 and beta is infinity. So then for node C, we have to update the minimum, that is beta value. Also node value, node C, so node C is 1. So then how do you update beta? Beta is the minimum of 1 comma infinity. Then what's the minimum value? 1. So alpha is 3 and beta is 1 for node C. So now alpha is greater than or equal to beta. So this node will be pruned. This path will be pruned. So now the node value of C is 1. So which pass the node value to upper node, that is A. So now for A already 3 is there. Now C is passing 1. So since it is maximum node, it has to find the maximum value. What is the maximum value of 3 comma 1? 3. So this is the final game tree which shows that nodes which are compared and nodes which are never computed. So hence the optimal value for the maximizer is 3 for this example. Okay, let us stop with this one.